transmission line, the voltage is a voltage or current. We consider only voltage, but the same thing applies for current. Same thing applies for current, and we found out that the voltage is propagating from left to right or from negative to positive. So there and from right to left, and we considered only the positive or the voltage propagating in the positive direction or from left to right. So B plus, that we consider the B plus. Now let us try to track the velocity of a fixed point on the wave. So that is what is that? That is a point of constant phase. A fixed point means a point whose phase is constant. Phase does not change. So let us fix that point as the crest of the wave. Instead of trough of the wave, you can take the trough of the wave or any point on the wave, but the crest is very prominent. Therefore, let us take that point on the crest of the wave. So that is the crest means maxima, trough means minima. So one of the maxima, why there are multiple maxima? Because there is attenuation. If there is no attenuation, alpha is equal to 0, then all maxima will be of same. So here, because there is attenuation, we have considered there is attenuation. We have not considered alpha to be 0, so we will consider it at any point, but it has to be crest, and that crest is constant. So that is not changing. That point is fixed. Now, if we consider that, then let us write V plus V plus ZT is equal to V0 plus exponential minus alpha Z into cos omega t minus beta Z plus phi, where phi is the phase. So phi is the phase. Now from this we will see that as the position changes or as the time passes, what is going to happen. Now we can set omega t minus beta Z is equal to constant. If we take, because why omega t minus beta Z is equal to constant? Phi is the phase, so phase is not going to change. So we have to take a constant phase. Because phase will be constant, then the point will be constant on the crest. So point will be exactly on the crest if the phase remains constant. So phi is constant. If phi is constant, then omega t minus beta Z is that constant. So omega t minus beta Z is equal to constant. So if we take omega t minus beta Z is equal to constant, then we differentiate both the sides with respect to time. So take the time derivative of both the sides. The left side will be omega minus beta dz by dt is equal to 0. So from this you can find out dz by dt is equal to omega by beta. Now what is dz by dt? You know from physics, you know dx by dt or ds by dt. Z represents the distance. Since distance, time derivative of distance is velocity, so dz by dt is equal to vp. So vp is equal to omega by beta. Now why we are calling it vpp? Stands for phase velocity. This is called phase velocity because we have considered a constant phase. Therefore this velocity is called the phase velocity. So vp is equal to omega by beta. If you expand it in the expanded form, this will be omega by imaginary part of gamma, and gamma, as you know, gamma is equal to square root of r plus j omega l into g plus j omega c. So bp is equal to omega by imaginary part of square root of two terms. First term is r plus j omega l, second term is g plus j omega c. Now we'll define what is called a characteristics impedance of the transmission line. So characteristics impedance is represented by Z0, and Z0, the characteristics impedance, when we are assuming that the wave is traveling in the positive direction, Z0 is defined as, by definition, it is equal to B plus by I plus. B plus, capital V plus by capital I plus, which is, we are not considering the time part here, only the spatial part, and the characteristics impedance gives you B plus by I plus. Now what is V plus? V plus is V0 plus exponential minus gamma Z. I plus is I0 plus exponential minus gamma z. So V plus by I plus is equal to V0 plus by I0 plus. So you can put Z0 is equal to V0 plus by I0 plus. So Z0 is a number. It is not a function of Z. Since V0 plus is the voltage at Z is when Z is equal to 0, voltage at that point. I0 plus is when the current when Z is equal to 0. So at a fixed point, we are considering a voltage that is fixed. At a fixed point, we are considering the current that is fixed. So their ratio will be fixed. So Z0 is a fixed number. It is a number and it is not a function of Z. So from that we know this. So I remember that Z0 is equal to V plus by I plus or V0 plus by I0 plus. Now let us use the first telegrapher's equations, which is dou V by dou Z is equal to minus Ri minus L dou I by dou T. And using the uh, exponential j omega t for dou by dou t, this expression becomes dv by dz is equal to minus ri minus j omega li. All b and I all are capital, which means we are not considering the time variation here. Time variation is cancelled out from both the sides. On left side and right side, you will have exponential j omega t, so they will cancel out, leaving out only the spatial variation or variation with respect to space. So dv by dz is equal to minus ri minus j omega li. Now that you can write, if I take minus I common, then the remaining part is r plus j omega l, that is z. So dv by dz is equal to minus zi. Now remember V plus Z is equal to V0 plus exponential minus gamma Z, and I plus Z is equal to I0 plus exponential minus gamma Z. Therefore, using this, you can say dV by dz, that you can write as minus gamma B0 plus exponential minus gamma Z, and that will be equal to minus Z into I is equal to I0 plus exponential minus gamma Z. Now you can cancel out exponential minus gamma h from both the sides, and you can find out V0 plus by I0 plus. That will do. So V0 plus by I0 plus is Z0. So Z0 will be V0 plus by I0 plus. That is called to Z by gamma. Now gamma is equal to root over of Zy. So there, that is Z by gamma is equal to Z by root over of Z into Y. Now that in the numerator you have Z, in the denominator you have root over Z. Therefore, this will be equal to root over of Z by Y, or root of whole of Y, Z by Y, two terms. Numerator is Z, denominator is Y. So that you can write. That is, you take the principal square root, and Z, you know what is Z, we know what is Y. Gamma is equal to Zy, that is in the first quadrant. Z0 is equal to Z by root over of Zy. So that belongs to the right half plane, and therefore Z0 will be greater than equal to 0, or Z0 is equal to root over of Z by Y, which is the principal square root. We are taking the principal square root. So using this value for Z and Y, once you use the value for Z and Y, next page. If you give the value for Z and Y, then Z0 is equal to root over of Z by Y. That will be root over of R plus J omega L by G plus J omega C. And R real part of Z0 is greater than 0. This is what you must remember. This is an important equation. Z0 is the characteristics impedance. Expression for characteristics impedance in terms of per unit resistance per unit length, inductance per unit length, conductance per unit length, and capacitance per unit length is the expression. This R root over of R plus j omega L by G plus j omega C. Now you have Vz is equal to V0 exponential minus gamma z. plus V0 minus exponential plus gamma z. Now we are considering wave in the both direction. General case, we are considering the general case. The red part is for the a wave in the propagating in the positive direction or the signal propagating in the positive z direction. The blue part is for the signal propagating in the negative z direction. Now, in the time domain, we will multiply exponential j omega t on both the sides. So, left side will be small v zt, small v as a function of zt. Right hand side will be real part of capital Vz into exponential j omega t. So, that you can also write in this manner. Uh, so, this will have b0 plus exponential minus gamma z into cosine of omega t minus beta z plus phi 0. And then the second term, which is the wave propagating in the minus z direction, that will be v0 minus exponential plus alpha z cosine of omega t plus beta z plus phi minus. Phi plus is the phase for the positive propagating or the wave propagating in the plus z direction, and phi minus is the phase for the wave propagating in the minus z direction. Okay. Now let us consider the backward traveling wave. Forward traveling wave we have seen, both the wave we have seen. Now let us consider the backward traveling wave. So wave is propagating in the negative direction. So we will consider I minus and V minus. Right. And if we consider I minus and V minus, the wave is propagating in the negative z direction, then Z0 here will be B minus Z by minus of I minus Z. Remember this, Z0 is equal to V minus by I minus. Now V minus by I minus, if you write that way you can say V minus by I minus is equal to minus Z0. Now, now the reference direction for voltage and current are to be chosen same as for the forward wave. Otherwise, there will be problem. If you take left to right as forward wave, then you have to take right to left as the backward wave. You cannot take left to right as forward wave and left to right as backward wave. That will be problem. So you have to consider the reference direction for voltage and current to be in the same direction, considering the forward wave. Okay. Now we'll consider the most general case. In the most general case, there will be a superposition of forward and backward traveling wave. Since there will be a superposition of forward and backward traveling wave, Vz will be V0 plus exponential minus gamma z plus V0 minus exponential plus gamma z. Then Iz will be 1 by Z0 V0 plus exponential minus gamma z minus V0 minus exponential plus gamma z. Now how you are going to get the second one? Iz expression shows you that Iz is equal to B0 plus exponential minus gamma z minus V0 minus exponential plus gamma z. This from where you get this minus term and from where you get this 1 by Z0 term. Remember that Z0 is equal to V0 plus by I0 plus. So that we know. So if we know that Z0 is equal to V0 plus by I0 plus, from that we can say I0 plus is equal to V0 plus by Z0 plus. So the first term is V0 plus by Z0 plus, that is same as I0 plus. I is equal to I0 plus exponential minus gamma z, that is the first term, forward term. Then consider the second term. Second term is I0 minus. I0 minus is equal to, from where you will get I0 minus, you know, Z0 minus, Z0 is equal to minus V0 minus by I0 minus, from which you can say I0 minus is equal to B minus of V0 minus by Z0. So put that If you put that, then minus V0 minus by Z0 is equal to I0 minus. So I0 plus I0 minus both have 1 by Z0. 1 by Z0 we have taken common. Then remaining term is V0 plus exponential minus gamma Z minus V0 minus exponential plus gamma Z. So this is very simple. You can use this simple thing. Okay. Now, we know what is Vz, we know what is Iz, everything in terms of V0 plus, V0 minus and Z0, everything we know. So, this is the basic formulas for the transmission line. Vz, expression for Vz, expression for Iz, then gamma is equal to alpha plus j beta, that is equal to square root of two terms. First term is r plus j omega l, second term is g plus j omega c. Then Z0 or characteristics impedance, that is equal to square root of two terms. First term, the numerator term is r plus j omega l, denominator term is g plus j omega c. Then guided wavelength lambda g is 2 pi by beta. Phase velocity Vp is equal to omega by beta. Attenuation in dB per meter is 8.686 alpha. So this summarizes the formulas, basic formulas for transmission line. Now we'll come to a special case, which is the lossless case. In the lossless case, in the electrical elements, there are two types of element. One is lossy element, one is power consuming element, where power is consumed, that is called lossy element. And one is power storing element, energy storing element, where power is not consumed, power is stored. Power consuming elements are resistance and conductance. Power storing elements are inductance and capacitance. Now, power consuming, because of power consuming element, there is loss. So if you do not want loss, then there should not be any power consuming element. So R has to be 0, G has to be 0. So in the lossless case, R is equal to 0, G is equal to 0. If you put R is equal to 0, G is equal to 0, then gamma, which is equal to alpha plus j beta, on that expression, if you put R is equal to 0, G is equal to 0, that becomes j omega root over of LC, which means alpha is equal to 0. And because it is only the imaginary part, there is no real part in gamma, it has only imaginary part. So alpha is equal to 0 and beta is equal to omega root over of LC. Then Vp, which is equal to omega by beta, that will give you beta is equal to omega root over of LC. So for beta put omega into root over of LC. So omega upon omega root over of LC. So omega will cancel out. So Vp will be 1 by root over of LC. That is Vp. Then Z0 characteristics impedance will be square root of j omega L by j omega C. And because R and G are 0, they will cancel out. Or there is no point in taking them. J omega in the numerator and denominator will cancel out. So Z0 will be root over of L by C. So remember this, Z0 is equal to root over of L by C, Vp is equal to 1 by root over of L by LC, alpha is equal to 0, beta is equal to omega root over of LC, gamma is equal to j omega root over of LC. So, so Z0 now becomes independent upon frequency. Earlier it was dependent on frequency. For a lossy case, Z0 characteristics impedance is dependent on frequency. For lossless case, it is independent upon frequency and real. Bp is independent upon frequency, or phase velocity is also independent of frequency in the lossless case. That is important. Okay. Now, suppose the medium between the two conductors, the two conducting wires, is lossless and homogeneous. Homogeneous means it is uniform and it is characterized by epsilon and mu. Electrically characterized. Characterized means electrically characterized. Epsilon is for permittivity, mu is permeability. Then LC is equal to mu into epsilon. Remember this. In that case, we will not prove it here. Proof will come later. LC is equal to mu into epsilon. Speed of light in dielectric medium CD is equal to 1 upon root over of mu epsilon. So that is same as 1 upon root over of LC, right? So BP will be 1 upon root over of LC, that is 1 upon root over of mu epsilon, that is equal to CD. So phase velocity is the speed of light in the dielectric medium CD. So Vp is equal to CD. Similarly, beta is equal to omega root over of Lc, that is equal to omega root over of mu epsilon, that is K, which is equal to K0 into root over of mu r epsilon r. What is K0? K0 is equal to omega into root over of mu 0 epsilon 0. As you know, epsilon is equal to epsilon 0 epsilon r. Mu is equal to mu 0 into mu r. So mu 0 into epsilon 0 root that into omega is called K0. K0 is the wave number in the free space. So in the medium, the electric medium, it will be K0 into root over of epsilon r mu r. Okay. Okay. Now let us come to another important part, which is the termination of the transmission line. Let us terminate the transmission line, which means at the end of the transmission line, we will put some resistance or capacitance or any combination of or some electrical element. So that is the termination. So we will terminate the transmission line. So transmission line, ending of the transmission line, there should be some element. At the end of the transmission line, there should be some element. So we'll consider the termination of transmission line. Now let us consider that it is terminated in an impedance whose that impedance is called the load impedance. The transmission line is terminated. The termination is, or we call the transmission line is loaded. Since it is loaded with an impedance, it is called the load impedance. So termination or loading of the transmission line gives you the load impedance. So terminating impedance or the load impedance is ZL. Now consider that ZL occurs at small z is equal to 0. Small z is equal to 0 means the position that we take the reference point at the right end of the transmission line. So from that point we will look towards the left end. Okay. Now Vz, you know, Vz is equal to V0 plus exponential minus gamma z plus V0 minus exponential plus gamma z. V0 plus is the amplitude of the voltage propagating in positive z direction at z is equal to 0. V0 minus is the amplitude of the voltage propagating in the negative z direction at z is equal to 0. Small z is equal to 0. Now this we can write as, and we can also write as V0 plus when z is equal to 0, that is equal to V0 plus V plus at z is equal to 0 is equal to V0 plus, and V minus at z is equal to 0 is equal to V0 minus. That we know. Now where we are assigning z is equal to 0, that we have chosen. Usually it is at the load that we have taken. Now with this concept we will consider other consideration. Other things. Now V z is equal to V0 plus exponential minus gamma z plus V0 minus gamma z. We can use z is equal to z0 as the reference plane here. So where you are going to find out the impedance, admittance, voltage, whatever you want on the transmission line. Z is equal to z0 is the reference point on the transmission line, and z is equal to 0 is the termination point or the load point. Small z is equal to 0 is the load point or termination point. Small z is equal to z0 is the reference point on the transmission line. You can write small z is equal to L, small z is equal to anything, small z is equal to B, whatever you want. You can write that, but I will take as small z is equal to z0. Now V0 plus z0 is equal to V0 plus exponential minus gamma z0. Similarly, V0 plus, you can write from this, you can write V0 plus is equal to V plus Z0 exponential gamma z0 on both the sides you multiply exponential gamma z0, then v0 plus is equal to b plus exponential gamma z0. B plus, when I say b plus, understand that it is v plus as a function of z0. Similarly, v0 minus will be b minus exponential minus gamma z0. Therefore, you can write v, which is equal to v0 plus exponential b is equal to v0 plus exponential gamma z. Now v0 plus is equal to b plus exponential gamma z0. So put that, then vz is equal to v plus z0 exponential minus gamma into z minus z0. Similarly, second term will be plus v minus z0 exponential of gamma z minus z0. What we have done is, you know, a to the power a to the power sorry, x to the power a into x to the power b is equal to x to the power a plus b, or x to the power a into x to the power minus b is equal to x to the power a minus b. The laws of indices, we are using that. Here x is equal to a, e to the power minus gamma z into e to the power minus gamma z plus gamma z0. So then you take gamma j minus gamma z, z minus z0 in both the cases that you get. Okay. Now compare these two terms. Vz is equal to b plus 0 exponential minus gamma z plus b minus 0 exponential plus gamma z, and Vz is equal to b plus z0 exponential minus gamma z minus z0 plus v minus z0 exponential gamma z minus z0. These are the two terms that you will comparing. Now, what does this imply? This imply that simply a change of reference plane has occurred from z is equal to 0 to z is equal to z0. That is what has happened. So, if you put z0 is equal to 0 from the second equation, you will get the first equation. That is what has happened. Otherwise, no difference. Both the equations are same equations. Okay. Now, we'll find out the impedance and at a distance L from the reference point, which is when z is equal to 0, there you have terminated, that is the reference point. From that, go to the left side. Therefore, at z is equal to minus L, we are going to find out the calculation, do the calculation. Now Vz is equal to V0 plus exponential minus gamma z plus V0 minus exponential plus gamma z. Now for z, if I put minus L, then V minus L voltage at that point at z is equal to minus L. So V minus L is equal to V0 plus exponential minus gamma into minus z minus L. So z is equal to minus L minus gamma into minus L is plus gamma L. So V0 plus exponential gamma L plus V0 minus exponential minus gamma L. So the first term is propagating forward, second term is propagating backward. Current similarly will be I minus L is equal to B0 plus by Z0 exponential gamma L minus B0 minus by Z0 exponential minus gamma L. L is the distance away from the load towards the left. Okay. And remember that this L is not the entire length of the transmission line. It can be the entire length of the transmission line. It may not be the length of the transmission line. It can be any point on the transmission line, but it is at a distance L from the reference point. Okay. Now we will define something called reflection coefficient. How we are going to define that? Let us see. V minus L is equal to V0 plus exponential gamma L plus V0 minus exponential minus gamma L. Now what we will do is, let us take V0 plus exponential gamma L common. If I take that common, then the first term becomes 1. The common term is outside the bracket. In the bracket, inside the bracket, first term is 1. Second term is V0 minus exponential minus gamma L divided by V0 plus exponential gamma L. Now exponential minus gamma L by exponential gamma L is exponential minus 2 gamma L. So that gives you this term, exponential minus 2 gamma L. The remaining is V0 minus by V0 plus. Now V0 minus by V0 plus, this term is called the load reflection coefficient. V0 minus by V0 plus is called the load reflection coefficient. Why it is called the load reflection coefficient? Because V0 minus is the voltage uh, at Z is equal to 0, negative traveling voltage at Z is equal to 0, and V0 plus is the positive traveling voltage at Z is equal to 0. So that is at the load, exactly at the load, the positive traveling voltage and the negative propagating voltage are V0 minus, V0 plus and V0 minus. Since they occur exactly at load, so therefore V0 minus by V0 plus is called the load reflection coefficient. But the total reflection coefficient is the total term V0 minus by V0 plus, which is called the gamma L, and gamma L into exponential minus 2 gamma L, that is called the reflection coefficient at Z is equal to minus L. Okay, so gamma minus L is equal to gamma L is equal to V0 minus by V0 plus, that is by definition the load reflection coefficient, and gamma minus L is equal to gamma L into exponential minus 2 gamma L. Now similarly, once you know the expression for V minus L, which is V0 plus exponential gamma L whole into 1 minus gamma L into exponential minus 2 gamma L. Similarly, for current, you will just divide that by Z0 and plus sign will be within the bracket, plus sign will be negative. Otherwise, current term is same. So voltage and current term you get. Now we have got the voltage and we have got the current at a distance L from the load. Since we have got the voltage and we have got the current, we can find out the impedance. Impedance is voltage by current. So ZL is equal to V minus L by I minus L. That is equal to, put the values. We know the expression, so put the values. If I put the values, then V0 plus exponential gamma L, that will cancel out from the numerator denominator. In the denominator, we have another denominator 1 by Z0. So that will now come to numerator. So that will become Z0. Then within bracket, we will have two terms, one numerator term, one denominator term. Numerator term comes from the bracket of the voltage. Denominator term comes from the bracket of the current. From the bracket of the voltage, we get the numerator as 1 plus gamma L exponential minus 2 gamma L. Denominator will be 1 minus gamma L exponential minus 2 gamma L. So that you can write as Z0 remains as it is outside, whole into 1 plus gamma as a function of minus L. Denominator is 1 minus gamma as a function of minus L. So for different minus L's, you will get different values. So ZL, expression for ZL in terms of reflection coefficient is this. This is the expression for ZL in terms of reflection coefficient in a transmission line, terminated transmission line. Now let us try to simplify this also. Now when L is equal to 0, then Z0 is equal to Z as a function of 0, L is equal to 0. So when capital Z0 will be Z0 or characteristic impedance of the transmission line into 1 plus gamma L by 1 minus gamma L, because once you put L is equal to 0, exponential minus 2 gamma L is equal to 1, because L is equal to 0. So that you can write as ZL. By definition, you write Z0 at Z is equal to 0 at the load impedance. So at the load, this is the impedance. ZL is called the load impedance. Capital L, Z capital L subscript L is the load impedance. Okay. So and gamma L, once you know this Z0 is equal to this, we know Z0 into 1 plus gamma L by 1 minus gamma L is equal to ZL. From that you can say 1 plus gamma L by 1 minus gamma L is equal to ZL by Z0. Then add 1 on both the sides, subtract 1 from both the sides, take the ratio, that will give you ZL minus Z0 by ZL plus Z0 is equal to gamma L, or gamma L is equal to ZL minus Z0 by ZL plus Z0. At any point, gamma as a function of L will be, and gamma subscript L exponential minus 2 gamma L. That we know. Okay, and now we are going to use that here. Z minus L, so impedance at a point L is equal to Z0 characteristics impedance into 1 plus gamma as a function of minus L by 1 minus gamma as a function of 1 minus L, that you can write as Z0 into 1 plus gamma L exponential minus 2 gamma L divided by 1 minus capital gamma subscript L exponential minus 2 gamma L. Now gamma L is equal to ZL minus Z0 by ZL plus Z0. Put that value. ZL minus Z0 by ZL plus Z0. Put those values for gamma L. If you put those values, then you get an expression for ZL in this form. Z0 into 1 plus ZL minus Z0 by ZL plus Z0 into exponential minus 2 gamma L divided by 1 minus ZL minus Z0 by ZL plus Z0, and that into exponential minus 2 gamma L. Now we will simplify that. If I simplify that, what we will do is multiply in the numerator and denominator ZL plus Z0. So do that. That is the first step. Multiply in the numerator and denominator ZL by Z0. Sorry, ZL plus Z0. So once you do that, then you take a then you multiply in the numerator and denominator. Then the next step is multiply in the numerator and denominator exponential gamma L. So if you multiply that, then the first term in the numerator, the first term becomes ZL plus Z0 into exponential gamma L. The second term becomes ZL minus Z0 into exponential gamma L into exponential minus 2 gamma L. That will be ultimately exponential minus gamma L. Similarly, in the denominator, you will get ZL plus Z0 exponential minus exponential gamma L minus ZL minus Z0 exponential minus gamma L. Now what we will do is, in the numerator take all the ZL terms common, similarly take all the Z0 term common. So ZL, if you take ZL common, then that will be ZL into exponential gamma L plus exponential minus gamma L, that is cos hyperbolic gamma L. So 2 times cos hyperbolic gamma L. Similarly, the second term, when you take Z0 common, that will give you 2 times sin hyperbolic gamma L. In the denominator also, you will get 2 times cos hyperbolic gamma L and 2 times sin hyperbolic gamma L. 2 in the numerator and 2 in the denominator will cancel out, leaving you out with Z0 into ZL cos hyperbolic gamma L plus Z0 sin hyperbolic gamma L divided by Z0 cos hyperbolic gamma L plus ZL sin hyperbolic gamma L. Now in the numerator and denominator, what you can do one thing, divide numerator and denominator by cos hyperbolic gamma L. So sin hyperbolic gamma L by cos hyperbolic gamma L is tan hyperbolic gamma L. So it simplifies now. Z at minus L is equal to Z0 into whole into numerator will be ZL plus Z0 tan gamma L, denominator will be Z0 plus ZL into tan hyperbolic gamma L. Now we will have a quiz will be given to you. The quiz is this: derive expressions for attenuation constant of a lossy transmission line and phase constant of a lossy transmission line. This is the quiz that you have to do at your home. Let us take it as a homework, or next time I will ask you this as a quiz. Okay, next. I think for today we have enough. Let us stop today. No. Next. So let us stop today. Next class we will consider other parts. If you have any doubts, please ask me, and I'll. Okay. Now let me come to the real part. In the next class, I'll give you a proper introduction. We are not introduced to each other, so we'll try to know each other in the next class. That is One point that I'll do, and I will supply you the class notes. What I discussed today, I'll supply you a PDF. Only thing is I do not know your email address.